Welcome everybody to this April presentation of our Bentley Bridge special interest group meetings. The topic of this week is rolling stock analysis for high-speed rail bridges. And we're going to be, of course, not only seeing the rolling stock, but as well defining what do I mean by rolling stock. Okay, so we know this is done through the interface of OpenBridge Designer, as we need to model the bridge first, right? And what we propose, if you're not familiar on what we do here, is that first we need to develop the 3D physical model of the bridge. When we do that in OpenBridge Designer, we can send this bridge to perform a structural analysis, a structural check, if you want to call it like that as well. So we're going to do the analytical and modeling. In this case, since it's going to be a rail bridge and we're going to be performing rolling stock analysis, then it has to be done through the RM Bridge software. Then, of course, we can send it back. And then when we have all the results, then we can create our documentation. And the documentation will be just basically what we call dynamic views or slices of the 3D model in different areas. So a slice across the deck of the bridge will be then, of course, a typical section, for example. And a slice across the pier, well, will be a pier elevation drawing, right? So, and then we can get all our quantities, reports, 3D plans, plans if we need detailing, right? And then all that information could be sent as well to construction, inspection, and planning, right? So all of these bridge operations are done inside and now complete solution, integral solution called OpenBridge Designer. OpenBridge Designer, it's a single software now, a single delivery in which includes the modeler, OpenBridge modeler. If we are going to design a concrete bridge, pre-stressed girder bridge, it will be Liebridge concrete. If it's a steel eye girder bridge, will be Liebridge steel. But in our case, it's a segmental bridge for supporting a railroad, so we need to design it using um, RM Bridge. Of course, with this software, we can design in a reality content, since the platform is MicroStation, so that we can take advantage of solutions like context capture, for example. Then, as we create this, we can modify our design, right? Taking advantage of changes in alignment profile of super elevation, for example, the bridge will react to it and move accordingly. We can integrate then multiple disciplines. As we finish my model, I need to detail it. Well, I can plug in Pro Structures and start my detailing process. I need a special visualization. So we have Lumen RT inside, so I can visualize my bridge and apply reality modeling techniques on that. Of course, if anything changes, of course, I can adapt to change very quick. If the alignment change, the profile change, I receive new super elevation, right? So the geotechnical conditions have changed. I receive new information from Ghent in which they complete all the soil borings that are requested, and I need to adjust the depth of the footings, or maybe even change from an isolated footing to a drill shaft because of geological or geotechnical conditions. So the software can adapt and move the bridge according to that, right? At the end of the day, what we want to do, of course, is improve our project deliverable. Not only plans, as we have been doing for the past, at least for me, 28 years, right? At the end of the day, we just deliver plans, but not anymore. Now we can deliver files for machine control. We can deliver files for fabrication, right? And then our model, the 3D model that we produce, is basically what we call now the single source of truth to collect all that information. And the plan sheets that we need to deliver are just now a representation, a 2D representation of that 3D model. So how we do this? Well, let's start the project, and we're going to create the bridge first for my railroad track. So what we're going to do here then, of course, will be to uh, create a DGN file, have an alignment, reference the terrain, and place a new bridge. I will create a new bridge. This case, I will select that this is a segmental bridge in this case, right? And just give it a name. So saying that, select the alignment where the bridge is going to go and place some support lines. So how many pier lines I'm going to select for that, right? Two, three, four. I mean, I can do it from, I can set up the bridge as final from the very beginning, or I can do preliminary studies and say, well, let's try five supports. Now let's try add one more, adjust the number of spans, adjust the span lengths as well. So nothing needs to be uh, fully defined or set in stone as I begin, because that's the idea of this adaptability to change. As I can add, move, modify, skew at any time I want. Right? So let's set this up, and I will just place the support lines for that. Done. So I got the support lines already set up. Right? So the next step after setting up the support lines is to uh, place the actual section itself. Right? So now it's going to be a segmental bridge. So for that, I already have templates created that come with the software, are fully parametric, by the way. So I can just do it, select one, and specify the spacing. You know, how many segments do I want? What spacing? You know, from one peer location to the next peer location, and just select how it's going to be the configuration, right? And the software will take care of laying out the peers, the segments, I'm sorry, following the alignment as well. So here, for example, by setting up, 14 segments at a certain spacing from the back to the ahead direction of the pier, right? And just select it and start completing and building up the segmental uh, cantilever bridge in this case, right? So I got one section. I can adjust. All piers may not be the same because of the different span lengths, so I can start adjusting them and just keep going and finish the entire bridge by that. One thing that I want you to keep in mind when I do this is that every time I build a new cantilever section, right, the build order increases. So, and this is the order that is going to be quote unquote activated when I go into OpenBridge for the stage sequence. So of course, when I go to OpenBridge as well, I can just change that, but then the OBM is keeping track on how I'm building this bridge. So assuming that that's going to build it on that same order, right? So at least it eases our input process when I go into the structural analysis part. So I continue with this process, right, until I just finish the complete bridge for that, right? And just at the end, I just need to apply in the gaps the closure port that I need, and I just have to select in each span how it's going to be closed until I will have, of course, the complete bridge built up, right? And I have my bridge already. The next step of that is when I have the cantilever, right, is to start placing support structures, right? So then I place the pier and select on the template that I want a specific pier that I just make created or is part of the library, up to you, right? And just select on each support line that I want to place the pier. And it knows automatically, of course, that it has to go below the segmental box that I just placed in. Maybe adjust some elevation constraints that saying that piers with the footing that is attached to, it goes 5 feet below the ground, 3 feet below the ground, 5 meters if it's in meters, and I just place it and adjusting to the ground elevations, I will just place the piers. Right? So one by one, you see two piers there because I'm looking at a skew, but now I have the pier complete. So I almost have the bridge now, right? So what is the next step? The next step on that will be to complete the bridge. So placing bearings, placing barriers if I need to, right? So I will just can do that, right? Or just now, basically send it to OpenBridge. It's a good place now to take this and say, I need to send the entire bridge that I finish, right? Fixing some of the supports or establishing the support conditions of each bearing for the proper analysis. Because what will happen here is as I'm sending my bridge to be computed analytically, OpenBridge automatically will verify or do a structural check. So now, also, let me announce that with OpenBridge Designer, the new version that we are releasing, OpenBridge is included. So all our bridge structural solutions are part now of OpenBridge Designer. So it brings the bridge that I modeled in the modeler in the MicroStation environment in a big model and became this now an analytical model. So it's part of the modeler now. It's all built up according to the stages. Remember the stages that we created, and the all the properties that is coming from model are transferred to RM. So internally, the software will does a structural check and verifies if the bridge model that I just created is kind of a structurally sound, at least for dead load, right? We can apply also seismic analysis there too, right? But it gives me all the information, right? Ready to do. Here it performs seismic analysis too because it does this as a response spectra first, right? You can change this method of analysis later, but I would say as a first pass of our design, we can check that if we have what we have built it on the modeling part is more or less compliant on what I need, right? And review the results, deflections, moments. So again, we call it this a structural check. There's not designing anything yet. It's a structurally check if your structure will preliminary be working, right? So the next step after that then now is to say, well, now let's dive into the problem of today. This is going to be a, railroad bridge, right? And it happens to be also that is a high speed one, right? So then what is rolling stock analysis, right? Rolling stock analysis is the study of the dynamic effects that my moving train, my high speed moving train will have on the structure. Um, so it's special forces that are happening, right? That they have to deal with comfort of the passenger on the rail cars. It has to be with movement in the structure, of course, and it has to be with fatigue with the structure. So there's different parameters that you got to take into account when a high speed train is moving along the bridge, right? Vibrations that I need to check and all of that. So that is what is all rolling stock is about it. At the end of the day, the theory behind it is time history, because as the train passes at high speed, we can analyze specific points on the structure, right? In which we can just report on that point the acceleration that is caused on the bridge, the velocity that is traveling to, and the displacement that is causing on that particular point, right? And of course, it's a special load as well, right? It's not only the speed, but it's could be heavy cars and different configurations, right? So it's not just applying when we talk about rolling stock. It's just not just like we apply our standard live loads when we design a regular bridge and we just place for example, the HL93 truck, right? And we just place the truck in different positions and analyze basically this as a low case scenario, right? A live low case scenario. This is actually happening because this is a dynamic effect of a vehicle passing a high speed. So it calls for we call it an intricate structural interaction. If it would be a normal case, so basically we can treat it as a vehicular load, right? So just applying loads on specific points and we're done. But this is different. It's happening at high speed. So these vehicles, the railroad cars, have high mass. They're happening at high velocity. So a standard load position doesn't do justice to what we need. And of course, passing a high speed, there is also vibration, actually resonance effects that we have to take care of on the structure itself, right? So then we need to include, of course, the dynamic effects because they causes dynamic stresses that are usually greater than just a static one. Excessive vibration on the structure, it causes, of course, uh, fatigue on the materials, displacement, or maybe even the ballast that or the gravel that is protecting the rail track. The displacement that could happen. All of that compounded too, because not only the material will be affected, the actual vehicle will be affected, but also the passengers that are riding inside that railroad cars. So that's why it's important the analysis of these rolling stock effects, right? So on a railroad bridge, as I said, not only we have to take care of the static forces that are happening, but as well the dynamics of that, and then of course the comfort of the passenger, as I mentioned before. So the problem gets defined as we need to account for additional, not only the typical loads that we use, dead loads, live loads, right? But then additional dynamic loads. Dynamic loads that need to change or the results will change depending on the structure, depending on the type of vehicle, in this case, the different type of trains that we may have, the speeds that they're going to pass through, right? And it has to talk a lot about the stiffness of the structures, the span lengths, of course, certain boundary conditions, and the heavy mass that is traveling at high speed. So we need to take that into account when we're going to analyze uh, this by rolling stock uh, calculations, right? So one more time, why is this analysis important, right? What we need to do it? Because, of course, as the structure vibrates, as high vehicle is passing, influences the track. The whole structure moves, shakes if you want it, right? And we need to account that because even the stability of the track could be in danger. There's a lot of moving pieces there, right? Now, and the worst case scenario will be that the actual rails, remember, is steel, it could start buckling and then be really a loss of safety could happen there. The critical situation, it's done by a certain formula, right? And that's in metric now, in which that frequency that we have to take care not to achieve is the velocity of the train, right? Divided by the average bogie distance, or basically the spacing between the railroad wheels, for lack of a better name. So when we run our analysis, we have to be careful on not hitting that frequency for because if not, I mean, we cannot proceed with the design anymore. That's basically our threshold point, or as we call it, the critical situation there, right? So then what is the performance criteria? Of course, when we design a bridge, we need to establish certain safety criteria, right? But here, when it's high speed, not only has to be the safety criteria for a structurally sound structure, right? But there are criteria, extra thresholds in which we define that it has to be a maximum vertical acceleration of the deck, you know, the maximum variation of cant or super elevation along the track, right? The end rotation at the supports and the horizontal displacement. So we have to watch out not only of the previous F value or frequency value, but also we have to watch out of not passing that threshold on these safety criteria that are mentioned on the presentation. Plus, as well, of course, additional checks, right? The deck acceleration, the stresses that we need to watch out for, maximum acceleration on the in coach, or basically maximum acceleration on the railroad car, because it has to be comfortable with the passenger too. There are certain limits that certain codes mention, right? Some of them say, for example, the acceleration cannot be greater than 5% of of gravity acceleration, right? So you have to be careful on when you do this analysis, double checking your results. You are not violating any of that displacement, acceleration. So that is what, when we run the analysis, we have to watch out for. And maybe a lame analysis or similarity could be, it's like, oh, the ride. Remember when you ride a car and you say, oh, it rides like a truck, or it's stiff as a tank. So you don't want to be stuck in a railroad car, for 2, 3 hours at high speed, feeling that you're driving a tank, right? It has to be a comfort for the passenger as well. So all of these parameters are important when you are designing these high speed rails, right? So now, what do we provide in RM Bridge that allows us to do that? Well, we have two kinds of calculations for rolling stock analysis. You know, uh, at the end is dynamic analysis. So, again, another analogy is like we're doing dynamic analysis, we're doing seismic analysis, but in a different way, because the seismic event, put it that way, is being caused by the railroad track. So then we will have, then following with the same analogy, is one method called the fast rolling stock analysis. That is just a model analysis. So let's see, kind of response spectrum, if you want to call it like that, right? So this is just passing the train fast and doing a linear analysis to check for very quick for the resonance detection and dynamic effects. Now, if you want a more refined analysis, so we apply as well the rolling stock analysis by using time history techniques, right? So then we can just eh, refine the calculations, assume even that the structure could behave non-linear in a certain at a certain times, right? So, if, of course, if it's a more detailed analysis, it provides better results, right? And the time integration is linear and non-linear too, accounting for what I mentioned, that the material behavior could be also behaving non-linear at a certain time. So, what we can do is create our bridge as we did, run the fast rolling stock, and if it's fine, so then just double check the design with the time history methodology without not much changing input. But now, if it doesn't work, or for example, all that criteria that I mentioned, right? Comfort of the passenger, maximum accelerations of the deck, displacements, and the frequency, right? If we can check it using the fast rolling stock, and if it doesn't pass, well, then I have to stop my design and come back and redesign the bridge, right? Without wasting further time doing the time history analysis. So then so also with the fast rolling stock, we can get critical points, and this use these points in uh, in the time history. Because remember, when we say at the very beginning, we just have to pick a point in the structure, right, to say where I want to check all these values for design. So when the fast rolling stock, I can just uh, run the analysis, and he give me some critical points that I can study and add this and apply time history to that particular point. So then I can reduce this time for analysis a lot, because I cannot, do this time history, for example, for every single point of the bridge, but do the most maybe active ones, or the ones that I think that it could be affected. For example, a high speed on a curve. So that's a point that maybe I also want to study, right? So, well, that's what the name is. This is fast. right? And this I can do really refined analysis, but the price to pay is time. Uh, well, no pun intended with the time history. Anyway, so how this is done? Let's see. I have my bridge, right? It's already structurally sound in OpenBridge. So the next step on that will be to just activate rolling stock. So here I can define first what train I want to run. So not only we provide when in our tool, we provide, or you can define their own train configuration that you want to run through, right? But we provide different cards already, standard ones. So uh, you can use that ones, or you can create your own. Not only that, you can run different uh, trains on the same run. So like here, for example, right? I'm selecting two different trains and also at different speeds. So I'm going to run this, for example, for that's in metric from 290 to 330 kilometers per hour, passing on the same point at an increments of 10 kilometers per hour, right? So it's not just running one train at what speed. I can do a range of trains with a range of speeds at the increments that I need, right? So basically, I set up the configuration for that. And then with the fast rolling stock, I just basically, after defining my trains, specify and say, well, let's run the analysis. So calculate it, and on the same run, what it's doing, it's passing the truck, well, truck no, train, it's passing the train, right, and calculating at different speeds. Now, this is one pass, for example. Now I am at 300 kilometers per hour, and it's evaluating at that particular point the acceleration, the velocity, and the displacement that that point of analysis that I'm looking for are going through, right? So, and then it will do that for that range of velocities that I specify, right? I'm building up a report that I can check, right? So this is doing more. Remember, I'm doing three different kinds of trains and at a range of velocities. And of course, now it builds up automatically a report. And that's when I have to go inside the report and start checking what happened, what are the maximum accelerations that happen, and if these accelerations that I obtain for these three different trains are within the threshold that I cannot violate, right? So right there, it could be saying that that is maybe not what you need, right? So I need maybe to change the design on that part, right? Because the threshold is what is 5% of the force of gravity. So this is a little bit more, right? So, and then also it gives me the critical points on where this is happening, right? And then I can go, right, to my rolling stock and then just decide that I need to do a more time history one, right? And just run this as well. So, and on that, I can go one more time and export all these results, right? And run this, send it back to the structural model, right? And be able to run it now using time history. So now this will be part of a new pre-processing inside RM now, right? Because I remember I finished with the fast one, right? So now I will take a particular case of that railroad or that rail track and make it part of a moving load analysis, right? And just do the structural calculations there. So then I can perform really a time history analysis with that particular element that I just chosen. So as I said, I'm extracting the results from the time history and send it back and make a part to the results and then make it as a moving mass analysis on that. And then do the time step calculations. Right? So one more time, recapping this is what I did is I run the fast rolling stock, and after that, uh, get the critical points where it's happened, isolate the train, and create a low case scenario of moving masses, send that information back to the structural part of the bridge, and then just run a time step analysis, a time history analysis of that particular moving mass. Right? And then one more time on that, the reports now check if I'm doing this, violating the maximum acceleration parameters that I mentioned a few slides back, right? If I can show it to you again, I need to double check if I'm not violating any of these parameters to proceed further with my design. So it's kind of a complex calculation, but if you think about it, using the rolling stock processor in OpenBridge, the generation of all that information is quite simple, right? Maybe I would say the tedious part will be to define the rail configuration if it's not already part of the software, right? But it's just like defining a new truck, obviously longer, but then it allows me to check for all of that and then continue with my design. So, and that's all I have for you today. You have any questions? I'm opening the chat window for that. So I'm gonna.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.